Welcome to the deep dive. Today we're plunging into, well, the often dizzying pace of AI development.
It really is something, isn't it?
Yeah, specifically we're talking about large language models, LLMs, and how they just keep getting bigger and, more complex. It feels like every other week there's a new model with billions, sometimes hundreds of billions, more parameters.
That's absolutely true. And for a long time, the main way really to boost their performance has been through what we call parameter scaling.
Hmm.
Basically, just making the models physically larger. We've seen models like DeepSeek V3 reaching a staggering 672 billion parameters.
Wow, that's an incredible amount of, well, raw power, but this incredible power came with a sort of a crushing cost memory. Imagine trying to squeeze something that big onto your phone. It's like trying to fit a supercomputer into a matchbox. And that's really the central challenge this new research is trying to tackle.
Precisely,
Yeah.
yeah. And if sheer size isn't always the answer, especially for AI on your device, what's the other main route researchers have looked at to make LLMs smarter?
Well, the other big approach is inference timescaling. This is where models try to enhance their reasoning by generating more internal reasoning tokens.
Mhm.
You can kind of think of it like the model talking to itself, step by step before giving you their final answer. GPT-o1 uses this kind of method.
Right, right.
But the catch here is that it can be incredibly time consuming. We even saw examples in the sources where a model generated up to like 900 reasoning tokens just to answer 2 plus 3.
900, wow.
Yeah. Clearly, that's not ideal for efficiency, and it often needs specialized training data to really make it work well.
So we're left with this clear dilemma. How do we make these LLMs even smarter, more capable, without just blowing up the memory requirements or slowing everything down to a crawl?
Exactly. And that's what we're diving into today. We're going to unpack a really groundbreaking new approach to scaling LLMs called parallel scaling, or parscale for short. We'll explore how it works, what new insights it gives us into, well, the very nature of AI, and why it could be a complete game changer for bringing powerful AI into low-resource environments, literally the devices in your pocket.
Okay, let's unpack this new paradigm then. Parscale.
Mm-hmm.
It doesn't just make models physically larger, like we talked about, or make them think step by step for longer. Instead, it increases a model's parallel computation. And it does this during both its training phase and its inference phase.
Parallel computation. Okay.
And the truly clever part, I think, is that it gets this boost in capability mostly by reusing existing parameters rather than
Yeah.
adding, a ton of new ones.
Huh, reusing parameters. So how does it actually do that? What's the mechanism behind it?
Right. So imagine your input. Say a question you ask the AI. Parscale takes that input and applies P, which just means a certain number of diverse and crucially learnable transformations to it.
Learnable transformations. Okay.
Then it simultaneously runs these transformed inputs through the same core model in parallel, multiple streams at once.
Ah, okay. Through the same model, but in parallel.
Exactly. And finally, it dynamically combines or aggregates all these P-parallel outputs into one single coherent output. It's sort of like having multiple versions of the same expert brain working on slightly different angles of the same problem all at once, and then blending their best ideas together at the end.
That's a great analogy. That makes sense. What was the spark for this? The inspiration? It feels kind of familiar, like something we might have seen somewhere else.
You're right, yeah. Its origin is actually pretty fascinating. Parscale was inspired by something called classifier-free guidance, or CFG. That's a technique used quite a lot in diffusion models, the ones that generate images, to improve the output quality.
Oh, right, for image generation.
That's right.
Okay.
Yeah. CFG typically involves doing two forward passes through the model and then combining them. The big innovation with Parscale is making both the input transformation and the output aggregation learnable processes.
Ah, making them learnable. Got it.
And crucially, applying this whole concept to language models for both training and inference. That's a really big step up from just, fixed tricks you only use at inference time.
Okay, so this isn't just a clever trick. There's a big underlying hypothesis here, isn't there?
Yeah.
What's the core idea about why this parallel computation thing could be just as impactful as simply adding more parameters?
Well, the central hypothesis is that scaling up parallel computation while keeping the model's actual parameters pretty much constant can enhance its overall capability. Well,
Yeah.
in a way that's remarkably similar to just scaling up the number of parameters directly.
Yeah.
It really challenges that conventional wisdom that, bigger is always better in terms of just the parameter count.
Right, the brute force approach. But then, did this theory actually hold up when they tested it? What did their large-scale experiments show?
That's the really fascinating part. So the research team did some preliminary theoretical analysis that suggested Parscale's performance measured by its loss, how well it predicts would follow a power law. Similar, actually, to the well-known chinchilla scaling law, which predicts how modern performance improves with more parameters and data.
Okay, so theory suggested it might work like established scaling laws.
Exactly. And to validate this, they performed really large-scale pre-training experiments. They trained models on 42 billion tokens from two pretty distinct datasets. One was StackV2, specifically the Python part, which is great for testing coding and reasoning. The other was Pile, which is a more general text corpus, good for things like common sense and memorization.
Right, diverse data sets.
Yeah.
And the big reveal, what did they find?
They discovered a new practical parallel scaling law. The results showed pretty clearly that parallelizing a model into p-streams is mathematically similar or equivalent in impact to scaling the model's parameters by roughly the logarithm of p. It's a O log p.
O log p. Okay, so you get a performance boost like a bigger model, but through smart parallel work instead of just size.
Precisely. And this wasn't just like a slight trend. Their findings lined up almost perfectly with the theory. We're talking incredible reliability, very robust. The goodness of fit, the R-squared value was up to 0.998.
Wow, 0.998. That's basically a perfect fit. So this new law seems really solid.
It does. Yeah.
Okay, so if this new law is solid, what does this all mean for, for you using AI in the future? How does Parscale actually deliver this game-changing efficiency and practicality?
Right. Let's talk about the superior inference efficiency, because this is where you, the user, would really see the direct benefits. Take memory, for example. For the same level of performance improvement, Parscale uses up to an astonishing 22 times less memory increase compared to just scaling up parameters traditionally.
22 times, that's huge.
It really is. This was seen for a 1.6 billion parameter model scaled up to P8, so 8 parallel streams, at a batch size of 1, which is typical for interactive use. And this massive drop in memory needed is because it adds almost no new parameters, only about 0.2% per stream. Really negligible, and it primarily expands something called the KV cache.
The KV cache, right. Can you quickly explain what that is and why expanding that is so much more memory friendly than adding parameters?
Sure, yeah. The KV cache is basically where the model temporarily stores the keys and values from its internal attention mechanisms. Think of it like a scratch pad for the current conversation or the input it's processing. It holds these cache representations. It uses far, far less GPU memory than adding entirely new layers or huge blocks of parameters to the model itself. So expanding it is a much, much more efficient way to handle the increased sort of thought process Parscale enables.
Okay, that makes perfect sense. Like using scratch paper instead of building a whole new wing on the library. And it's not just memory, right? You mentioned speed too, latency.
Exactly. For that same performance level, Parscale also shows up to 6 times less latency increase. Latency being that crucial delay, between asking a question and getting the answer.
6 times less delay increase. Nice.
Yeah. And this efficiency comes from its GPU-friendly parallel computation. Modern GPUs are built for parallel tasks, so these streams can be processed very quickly, simultaneously.
So this sounds amazing for running models on your phone, maybe in your car, robots, whatever. But what about the other big hurdle? Training these massive models in the first place. Does all this clever parallel stuff make training way more expensive?
That's a really fair question. And yes, Parscale does introduce more computation during the training phase itself. But the researchers came up with a pretty clever two-stage training strategy to help manage this.
2 stages, okay.
Yeah.
How does that work?
So in the first stage, they do traditional pre-training with the vast majority of the data. Let's say, for example, 1 trillion tokens, standard stuff. Then in the second stage, they apply a Parscale training, but only with a much, much smaller amount of data, maybe just 20 billion tokens, which is only, 2% of the data used in the first stage?
Only 2%. Wow. And does the model actually pick up the Parscale approach quickly in that short second stage?
Apparently, yes. What's remarkable is how quickly the models seem to adapt to Parscale in this second stage. It shows it's rapidly effective, and this approach significantly reduces the overall extra training budget you might have worried about.
That is clever, so it minimizes the extra training cost.
Exactly. And this flexibility also extends to how you can apply it in the real world. You don't necessarily have to train from scratch with Parscale. It can actually recycle off-the-shelf, already pre-trained models they mentioned, using Qwen 2.5 as an example, just by post-training them with Parscale for a bit.
Oh, nice. So you could potentially upgrade existing models.
Potentially, yes. Or it can be used in what are called parameter-efficient fine-tuning settings, or PEFT. These are smart techniques to adapt big models for specific tasks without having to retrain everything from the ground up. Parscale fits in there too.
Okay, and you mentioned something earlier, dynamic scaling. There's another really cool feature here impacting flexibility, dynamic parallel scaling. What does that actually mean for someone deploying these models?
Right, dynamic scaling. It essentially means you can flexibly adjust the number of parallel streams, that p-value we keep talking about during deployment, on the fly.
Ah, so you're not locked into one setting.
Exactly. Your model can dynamically adapt its capabilities based on the situation, without changing the core model weights at all. Maybe you need high throughput to process a big batch of queries quickly. You could increase P, or maybe you need the absolute lowest latency for a quick single-user chat. You could decrease P. This adaptability in real time is incredibly powerful.
Yeah, that sounds super useful. This whole research area seems to be getting at a really fundamental question in machine learning, doesn't it? Like, is a model's ultimate power, its capacity, determined mainly by its sheer number of parameters, or is it more about the amount of computation it performs and what's their relative importance?
Absolutely. Traditional models often scale both parameters and computations somewhat together, making it really hard to disentangle their individual effects.
Right.
Parscale, by focusing on scaling computation while keeping parameters almost fixed, gives us a new lens to look through. And it leads to a really insightful conjecture or hypothesis. The idea is that model parameters mainly impact a model's memorization skills, basically, how much stuff it knows or can recall accurately.
Okay, parameters for memorization.
While parallel computation primarily impacts its reasoning skills, its ability to actually process information, connect ideas, and derive new conclusions.
Memorization versus reasoning. That's a fascinating distinction. Is there concrete evidence in their results to back this specific idea up?
There is, yeah, and it's pretty compelling stuff. They found that Parscale yields much more substantial improvements on tasks that are known to be reasoning intensive, like coding and math problems. For example, they took a 1.8 billion parameter model, trained it on 1 trillion tokens, and then scaled it to P8 using Parscale. It showed a huge 34% relative improvement on GSM-8K, that's a benchmark for math reasoning, and a 23% relative improvement on MMLU, which is a broad, general reasoning task set. Much bigger gains than on pure recall tasks.
34% on math reasoning.
Yeah.
Just from parallelizing. Wow. So if I'm understanding this right, a model using Parscale, even with fewer parameters, could potentially match the reasoning abilities of a much larger traditional model, even if its pure memorization, its factual recall, isn't quite as encyclopedic.
That's precisely the implication, yes. And they give a concrete comparison that illustrates this really well. A 1.6 billion parameter model using Parscale with P8. So 8 streams could achieve coding abilities similar to a traditional parameter-scaled model with 4.4 billion parameters.
4.4 billion, okay.
But its performance on more general tasks, which rely more heavily on memorization, was only comparable to a traditional model with about 2.8 billion parameters.
Ah, okay. So great reasoning boost, less dramatic memorization boost. That really seems to support the hypothesis.
It does. It strongly suggests parallel computation is specifically enhancing that reasoning faculty. Plus, they also found that larger models actually benefit even more from Parscale. The performance improvements from adding parallel streams got bigger as the base model size increased, which again suggests computation becomes increasingly valuable for capability as models grow.
Interesting. So this Parscale sounds like a pretty unique approach. How does it fit into the broader AI landscape? How is it different from some other methods we've maybe discussed before that people might be familiar with?
Yeah, it's good to clarify those distinctions. For one, it's definitely not the same as those other inference timescaling methods we touched on earlier. Things like chain of thought prompting often scale serial computation, making the model think step by step for longer. That can lead to inefficiency and high latency, like that 900 token example. Parscale, crucially, scales parallel computation efficiently.
Right, parallel, not serial. And while you said it was inspired by classifier-free guidance CFG from image models, it goes quite a bit further, didn't you say?
Yes, absolutely. The key difference is that Parscale makes the input transformation and the output aggregation learnable. The model learns how to do this optimally. And it's applied during training, too, not just as an inference trick. That's a huge difference because it allows the model to fundamentally integrate this parallel processing into its workings.
Makes sense. And finally, just to be clear, how is this different from just, say, running multiple different models and combining their outputs like a traditional model ensemble?
That's another important distinction. In a traditional ensemble, you usually have separate models, maybe trained differently, that don't share parameters. They are independent. ParScale's parallel components, however, share most of the parameters. They are running through the same core model weights. This parameter sharing is absolutely key to its memory efficiency. You're not duplicating entire giant models.
Got it. Shared parameters, learnable transformations, parallel processing during training and inference. Okay, so to kind of wrap up our deep dive into ParScale here, it really offers a novel and seemingly highly efficient new way to scale LLMs. It seems particularly beneficial for deployment on, edge devices, phones, cars, etc., because it emphasizes parallel computation over just adding billions more parameters.
Right. And beyond the practical benefits, it also gives us these profound insights into the potentially distinct roles of parameters versus computation and what makes these models capable.
Mm.
Maybe one leans towards memorization, the other towards reasoning.
Which leads us to our final thought for you, the listener.
As artificial intelligence becomes more and more widespread, and we really start to envision LLMs moving off giant centralized servers and onto the devices in our pockets, our homes, our cars, what new possibilities does this shift in thinking, moving away from just bigger is always better towards smarter, more efficient computation might be key? What possibilities does that unlock for the future of AI?